Yeah, welcome back to the lecture series on analysis of indeterminate structures. 18 CV 52 code. We are in module 4th, lecture number 39, presented by Professor Girish Chalagari, Department of Civil Engineering, KLS VDIT, Halaya. In the previous class, we have studied about the analysis of the plane truss, which is solved by flexibility method. We took a question from previous question paper, that is from January 2020, and we solved it. We found the forces in all the members. We analyzed the frames and we completed it. In today's class, once again, we are continuing with the bent frames, which will be analyzed by flexibility method. So it is quite different from the till today what we have done, because the method is same, the procedure remains same. Only a thing that redundance what we take, those will be in the form of integrations. Here the integration part will be taken into account. So whatever we solve it by integrations. So when a frame is asked, whether it is bent frames or a whole frame is asked in the analysis by flexibility, this method should be adopted. So let us take one small frame, that is half frame. So we will solve it and we will come to know what will be the method when frames are being given to solve by flexibility. So analyze the rigid frames shown in the figure by flexibility matrix method. Draw a BMD and SFD. So here we can see, guys, bent frame is there, ABC, with A and G is hinged, having two unknown forces, and C is a fixed one having three unknown forces. And we can see the length of column is 4 meters, that is B to C, with a model of rigidity I, while the AB member is subjected to two loads. One is the entire beam is applied by UDL of 40 kilonewton per meters, and the total span of AB is 12 meters, and a point load of 270 kilonewton is applied at a distance of 4 meters from joint B, and the modulus of rigidity for member AB is given as 4 meters, 4I. So I is 4 times I for AB and 1 time I for BC. Span is 4 meters for BC, and for beam it is 12 meters. So first let us know what are the statically indeterminates, what are the degree of redundancy here. So we can see from the diagram itself, A joint is having two unknowns, that is VA and HA is the unknowns here. We have, as I shown in the diagram here below. HA and VA is unknown at A point. In the similar fashion at C point, we have three unknowns, that is vertical force at C, horizontal force at C, and moment at C. So total number of forces which are unknown in these joints are 5 numbers. And we know that we have an equation of equilibrium of 3 numbers. So 5 minus 3, 2 is the degree of redundancy or statically indeterminacy. So now the question comes, which are the two forces in this diagram to be removed and make the frame, bent frame, statically determinate, then finding the deflections at joints where we have removed the forces. Then we apply a unit load, unit moment wherever we have removed the force. Then once again we find the deflection due to the applied load or applied moment at the required point. So here I am choosing a vertical force at A and horizontal force at A, that is VA and HA as a redundancy force. So when we remove the redundancy of both the forces at A point, it becomes a cantilever one. So cantilever means fixed at C point. B is also rigid joint. So A doesn't have any forces. We can see in the diagram here shown clearly. ABC, A is having no forces, and AB is subjected to a UDL and point loads, and C is fixed. So this is a determinant structures of a removal of the forces. Now, vertical force at A is taken as first coordinate, and horizontal force at A is taken as a second coordinate points. Now, first, due to these determinant structures, draw a free body diagram for AB and CD, BC. So we are splitting AB here. Once we split AB, we take out the AB point. We can see A's don't have any forces here, but B is a rigid joint. We'll have forces at this point. So a point load of 270 is applied at a distance of 4 meter from B, and entire beam is subjected to a load of 40 kilonewton per meter. So what could be the forces at B here? Because B is the one joint where it is continuity is there. A is the released structure, so we can't get any movement or forces at A joint. Whatever movement forces that should be calculated at the B joint here. So at a B joint, we can know what are the vertical forces at summation of vertical force at B equals to what? 40 into 12, that is UDL, plus 270 is point load. So total vertical load at a B joint will be 750. We can see the 750 is acting downwards in beam. So to counteract this, to make this beam in stable condition, the load of 750 kilonewton should be upward at a B joint. Suppose if you apply 750 as a B joint in the upward direction force, then the beams become stable. There is no chance of failure of beams. In the similar fashion, the moment at B, what could be the moment at B here? Again, that you should know. Moment at B will be 40 into 12 into 6 plus 270 into 4. So the total moment anti-clockwise acting at a B joint will be 40 into 12 into 6 plus 270 into 4. We get 3,960 as a kilonewton meter moment at B joint in the anti-clockwise directions. And we know that the vertical force is acting downwards. So in order to keep this vertical force and movement in a condition to make this frame stable one, the opposite direction and opposite movement should be generated at B joint due to this load. Let me make you clear that whatever load is coming down, whatever movement is generating at B point, due to this external load, the same quantity of movement, the same quantity of force will be in the opposite direction at joint B to keep the member in statically determined function. That's what we can see the diagram here. AB with the UDL with the point load. As I told, the vertical load is 40 into 12 plus 277, 50 is the downward force. So keep it in mind. Upward force of 750 will be generated at B joint to make the beam stable. In the similar fashion, we can see there is an anti-clockwise movement of 3,960 that we can see here. 40 into 12 into 6 plus 270 into 4, we get 3960. So this is in anti-clockwise. To keep it in balance, their clockwise movement of 3960 will be present at B joint. So this is a free body diagram of member AB. Similarly, for member BC, B already we found the force and moment here. So at a B joint, to keep this in stable, as I told, BA, you can see the equation of joint equilibrium equation that is we found in first module, that is analysis of trusses. That is joint equilibrium equation is the summation of moment meeting at a single joint should be equals to 0. So the moment at BA, the moment at BC equals to 0. So whatever moment we got for BA, the same will be for BC. In the same fashion, and we split the members when we draw the free body diagram for the individual one. Here the calculated moment and forces we got at B joint. The same in the opposite direction will be there at B joint when we consider member BC. So when we consider BC, 750 was upward, 750 will be downward, so that the beam will be stable. The clockwise movement is 3960. We get an anti-clockwise movement of 3960. this is what we have got. And the free body diagram of the C joint will be 750 upward and 3960 in the clockwise direction, opposite of this one. So this is a free body diagram what we have drawn for the external load. Then since we have removed the redundant force, we are applying the unit moment or unit force in the same direction in what we have removed. So first coordinate joint is A point. We have removed the vertical force VA, which was acting upward. So here we are considering a small truss, small bend from ABC with a unit load 1 kilonewton applied in the upward direction at A joint, which represent the vertical force at A. So when we apply this load, let consider a point joint as a D here. So we can split member AD, DB and BC by finding the moments. Due to unit load applied at A point, the moment, the load generated at B point will be 1, which is moving upward. So definitely there will be a downward force of 1 in the B joint. In a similar fashion, you can see 1 into 12, it is acting 12, it is acting clockwise direction. So to keep the member, the joint in balance, the anti-clockwise movement of 12 kilonewton is applied at B joint. So how we got this 12? That is 1 into 12. This is clockwise, so anti-clockwise will be there in the opposite direction. So this is a free body diagram for member AB and BC and a unit load applied in the vertical direction. So when we come to BC, as I told, generated value moment and value is there. In the opposite direction, it is moving downward, so there will be upward force of 1 kilonewton. And this is anti-clockwise 12 kilonewtons, so we get a clockwise 12 kilonewton at a B joint. And C is not needed, it will be a fixed end. So this is a free body diagram for member AB and AC when we applied a unit load in the vertical direction. So similarly, the second coordinate, that is horizontal force. So we are applying a unit load in horizontal directions. You can see here the free body diagram of AB and BC will be in this form. When we apply unit load in the direction of flow itself, so there is a opposite flow at a B point. Similarly, opposite of this will be at column base. So column is having a load of 1 kilonewton at top of column, and at the bottom it is 4 kilonewtons. So this is what we have got the free body diagram for member force applied in horizontal direction. So once we draw the free body diagram for all this is capital delta 1, this is small delta m1, this is small m2. So we can form a table here like this. Particulars we can say, other we can take my members here. That is AD, DB and BC. Many of say, since we cannot consider D joint, we can directly take B joint. What happens? There is a point code of applied at D joint. If you directly take at this point the moment, the length between this point and this point is 4 meters, but it is we consider for the whole length. So we need to split the beam where we get a point load here. So that's what we have taken member AD, DB and BC as the 3 members subjected to a load. So while we form a table, what are two things to be written here? Flexure rigidity, we need to write, that is 4 times I given at AD and 4 times I given at DB. For BC it is 1. Similarly, the origin what we occupy is at AD point, A will be the origin. For member AD, A will be the origin. For member DB, D will be the origin. For member BC, B will be the origin. So once we get the origin, member A to D is there. You can see member A to D. So the limits will be from 0 to 8. 0 is A point, at D you should travel 8 meters. That's what the limit for A to D distance is, 0 to 8 meters. The distance of origin is B point here. So the distance between D to B is 0 to 4 meters. Similarly, for member BC, B is the origin. The distance between B to C is 0 to 4 meters. That is the limit that is given here. This is how we got the limits. Next comes the M1, M2. Capital M, uh, the moment due to the external loads applied over the members. M1 is the unit load applied at a direction in upward, for which we get the deflection in the members that will give M2 values. Then M1 value. M2 is the horizontal force what we applied at the coordinate second point and finding the deflection at the required points. Why this M1, M2 is required? As I told, we need the equation here. This equation we required. P into delta, small delta, capital delta minus delta L. So to have this, we need to know the forces here. So which are the forces here? We can see here. P is nothing but the unknown forces. That is, one is vertical force, one is horizontal force. That is VA, HA. Delta, we need to know the delta here. So delta deflection at one point due to the external loads, unit load applied in horizontal direction. And delta 22 is the unit load applied in the direction of horizontal due to the requirement. So delta, there is no external moment. Even small delta even is nothing but we can see here how we find this delta M. That is capital M into M1 will give 1 delta 1. The delta 2L will be capital M into delta M2 into divided by EL. So what is M1, M2? M we can see here. We have drawn the free body diagram here. So once we talk A to D is a distance 0 to 8 I have given. Take a section in between AD at a distance of X from A because origin is A here. For member AD, A is the origin. So we are taking section at any distance in between AD at a distance of X. So moment what we got at this access point will be 40 into X by 2. We are taking a section moment at this point will be for member AD will be 40 into X by 2. Since this is anti-clockwise direction, we will take it as minus here. So for member AD, for capital, the moment will be minus 40 into X by 2. That is minus 40 X square by 2. Next, we are taking member P to D. We are considering B as a origin. Even we can consider A as a origin, no problem. But we are considering B as a origin. So the distance between B to D is 0 to 4 meters. So let us consider at a section X from B here. Already we know the force at B point. One is 750 upward. Clockwise is 3960. So when we take a section at 22 in between BD, the forces will be 750 into X. This is the right hand side. Anti-clockwise become plus. So 750 into X minus of 3960, which is clockwise in the right hand side. So 750 into X plus 750 into X minus 60 minus of UDL in between the X value. UDL is 40 minus 40 into X by 2. This is equation for the second. I told 750 into X minus 3960 minus 40 into X by 2. This is for member DB. Similarly, for member BC, you can see here a BC momentization section is taken in this point. You may ask question why I can't take from C to B. Because C is having 3 unknowns, it becomes difficult to know the forces. That's what P is taken. P is having a load of 750 downwards and a moment of 3960. When you take a section at this point, plus 3960 will be the moment at C job. C minus 3960. Similarly, the first unit load applied at A point for member AB, when we take a section here, 1 into X, that is clockwise. So plus X will be there. Similarly, for the second one, B is here. B to D, when we take a section at this point, 1 into X, that is clockwise, right hand side minus 12 will be there. So 12 minus x will be the formula, 12 minus x. Then coming over to third one is clockwise, right hand side. So for number B to C, we get minus 12. Okay. So M2 is nothing but a horizontal force applied over the member. So we can see here, when we apply unit load at horizontal sections, and at a section between AB, the moment will be 0. We take a section at B to D, we get 0 force because it is moving on axis. Then the opposite force, when we consider member BC, you can see at a B joint there is a load of 1 kN in the opposite direction. So when you take a section at this point, it will be 1 into x. Clockwise at right hand side it is minus x. So we have shown here. Once we get this table, we can substitute the values like this. To find delta 1L, integrate capital M into small m1 into dx by EI. Similarly, delta 2L, we can see here, we can integrate capital M into small m2 into dx by EI. Capital M is due to external loads, m2 is due to second coordinate unit load applied. Similarly, this capital 1 delta L, 1L, delta 2L we get from these two equations. Substitute value of M and M1. This is M value, this is M1 value. Similarly, we can see first one we find delta 1L here. So delta 1L equals to first equation we are writing for M into M1. So M is what? For member AD, the limit is 0 to 8. Integrate 0 to 8 minus 40 into x by 2 delta 1L. Integrate 0 to 8 minus 40 into x square by 2. 2 and 40 cancels, only 20 is left, minus 20 x square into m1 is x into dx by 4 ei, because visited is 4 times I, so it is 4 ei, we can see. Similarly, for member AD, we can write equation. The integration with respect to the limits is 0 to 4. The formula for the capital M is 750x minus 3960 minus 20x square bracket. For a small m1, it is 12 minus x whole divided by 4 times ei. Similarly, for the third member BC, limits for 0 to 4, we can see minus 3960 is the moment for external loads. Then for a unit load, the moment you install here divided by ei. The same thing we have substituted, we are integrated, what we get 420. 5 is left, 5 into x cube dx by ei. So minus 5 into x raised to 4 by 4, 0 to 8 will be the limit. After integrating this with this, we get 5 into bracket of x raised to 4 by 4 into 0 to 8. This is I am taken minus. Integrate 4752 into x raised to 4 plus 2250, that is multiplying this equation with these equations, we get this long equation. Once we get this equation, integrating with respect to dx and with the limits of 0 to 4, we are getting the final 1 delta 1L value will be minus 2,21,850 by EI. Similarly, we get delta 2L. Delta 2L is capital M into small m2 by dx. Capital M, we can know that this is capital M. M2 at first member AD and BD member, it is 0. There is no force. We have force only at this one. So these two become 0. Left with the final one equation. So delta 2L equals to 3960 into x. You can see here. 3960 into x by dx by ai. So what we get is 3960 into x square by 2, 2 gets cancelled. X substitute value of x is equal to 0 to 4. The delta value we get is minus 31 680 by EI. So this is how we get delta 1L and delta 2L. Next, we got capital deltas. Now small delta. Small delta is how we get the equation small delta. We can see here. Small delta 1 equals to m1 square. That is m1 into m1 into dx by EI. Then delta 1 2 or 2 1. We get integration of m1 into m2 by dx by EI. Finally, the last integration, that is small delta 2 2. We get integration with m2 into m2 dx by EI. Substitute the value of m1 and m2 at respective points as per the given integrations. So we can see here delta 1 that is m1 into m1. So m1 into m1, we are substituting the value. You can see the first integration is 0 to 8 limit. X is a given value. We can see here x, I am taking m1 square. This is x is given. So that will be x square by 4ei plus 0 to 4 second limit, that is member db minus x plus 12 into 10 square divided by 4ei plus the third member 0 to 4 integration 12 square by ei. So integrating this x raised square by 4 will be x raised to cube by 3 by 4ei, that is 12 x cube by 4 integration with respect to 0 to 8. So this will be x square plus 144 minus 12 into 2, 24 into x. So 144 into x raised to x, integrating we get, plus we got 144 into x raised to divided by 4, x raised to cube by 3 minus 24 into x raised to square by 4. Finally, delta 1 we get as 720. When we get delta 2 or delta 1 at integration of m1 into m2, in m2, two members are 0, AD and DB, left with the last member DA having a value of x here. So m1 into m2, m1 at the last member will be 12 here, and m2 will be x. So 12 into x we can see here. These two are 0, left with the 12 and into x. So 12x, that is 12x is nothing but a 12 into x cube square by 2. So 2 gets cancelled, substitute x is equal to 4 here, we get 96 by EI. Next, coming to delta 2. Delta 2 is nothing but a integrate with respect to m2 into m2. So m2 into m2 means m2 is nothing but first two members AD and DB are 0, left with the last member that is B to C. We get B to C is nothing but x here. So x into x, x square into 0 to 4 the limit into dx by EI. Substituting valuing x is equal to 4 here. So x cube by 3 under raised to the limit of 0 to 4. We get 4 raised to cube by 3. We get 21.33 as a delta 2 value. Once we get the small delta and the delta values, substitute this all in the flexibility matrix equation, that is compatibility equation, that is P into small delta is equal to delta minus delta L. So P is the unknowns, vertical force and horizontal force. Delta is 96, 21.33 is equal to delta, it is 0, minus of 221850 for delta 1L, and delta 2L is 31680. Substituting this value, we can see 720 into R1, 96 into R2, minus into minus plus 221850. Similarly, 96 R1, 21.33 R2 is equal to minus into minus plus 31680 as the issue. Using your calculators, calculating all this, the value for R1 and R2 we get is, the vertical force we get is 275 by EI, and the horizontal force what we get is 246 by EI. So this is what when it is given with frames, whether it is band frame or full frame, the methods remain same. Only a thing that here we go with the integration method. This formula is same. Only friend is falling of delta L and small delta. For that, we need to go for integration method. So integration, first only we can see here, capital delta 1L, capital delta 2L. If third one is there, it will be capital 3L. So capital M due to external loads, M1 is due to unit load applied at first coordinate. Delta 2L is, capital M is for external loads movement, and M2 is the movement due to the unit load applied in the second coordinate. This is how we get delta 1L, delta 2L, and for remaining delta 11, delta 2L, we have these small values. Before knowing this, forming of this table is very important. To form this table, first we need to draw the free body diagram of individual members. So how you draw the free body diagram? You can see here, when you take a member like this, split AB and BC, AB and BC are split. Since A is free and B is fixed, find moment and forces at B. F1 forces and moment at B. The same moment and forces will be there in the opposite direction of column. So the same force will be in the opposite direction. Then we get this free body diagram. Similarly, applying unit load at A, we draw a free body diagram. Applying unit load at A in horizontal direction, we draw a free body diagram. This is how we are drawing free body diagram. Then we are finding the table. Before table, one thing I want to clear here, when you draw free body diagram, I want to clear one more time how you get the force and moment. As I told, A is free and B is fixed. Exit 1, every moment will be at this point. 1 is summation of vertical force. I told 40 into 12 plus 270, 750. Actually, 750 is coming downward. To stay, to keep member in stable, there should be opposite force of same value. 750 is acting at B point in upward, which makes this member be stable at this section. Similarly, when we take moment at B point, 40 into 12 into 6 anticlockwise, 270 into 4, it is also anticlockwise. Both when we add anticlockwise, we got 3960. This is the actually movement applied at B joint in the anticlockwise. To keep it in stable, clockwise movement of same dimension should be applied at B, that is 3960. Whatever force we get downward 750 here, anticlockwise 3960 at B point for the second. This is how we are going to draw the forces. We are going to calculate the forces and the moment when we are going to draw the free body diagram. So here also same, apply unit load. You can see at B it is splitted here. 1 into 12, 1 upward, 1 downward. Movement will be 1 into 12. It is clockwise direction. 1 into 12 will come and like this in clockwise. To resist this, a minus of 12 is applied at this point. Opposite of these forces will be there in member BC. Same concept is applied for everywhere. Then we are drawing this. That is flexure rigidity, origin, limit, M, M. Unless and until we understand this concept, it may be quite reliable, difficult for our students to understand the things. But we don't have any option here. You look into your question papers, look into your books, practice the things. If any doubts are there, you may come more and ask us. Okay? Yes? Anybody is having any doubts here? Yes, students? Is anybody having any doubts? If you people are having any doubts, we will conclude the things. If no doubts, we will conclude as it is. If doubt, we will solve it. And these will come into your doors unless you try it or you practice it. Only by looking into the things, going through the glance over the papers, you will not make you understand the things. Once you start following it by your own, by taking pen and paper, then only you will come to know exactly what problems you are facing. Yeah. So, shall we conclude or we will close here only? Hmm? Yes. So we will conclude here only.